One of the biggest creators of modern-day physics was an Italian astronomer named Galileo Galilei. He provided a number of scientific insights that laid the foundation for future scientists. His investigation of the laws of motion and improvements on the telescope helped further the understanding of the world and universe around him. Both led him to the question and the current belief at the time that all things revolved around the Earth. During Galileo's time, it was still understood that heavier objects fell faster than lighter ones, but Galileo was not convinced. He experimented with balls of different sizes and weights, and he rolled them down ramps and various inclinations. His experiments revealed that all of the balls boasted the same acceleration independent of their mass. He also demonstrated that objects thrown in the air travel along a parabola. Galileo also worked with pendulums. In his life, accurate timekeeping was virtually non-existent. Galileo observed, however, that the steady motion of a pendulum could improve this. In 1602, he determined that the time it takes a pendulum to swing back and forth does not depend on the arc of the swing. Near the end of his lifetime, Galileo designed the first pendulum clock. Galileo was also incorrectly credited with the creation of a telescope. He did not create it, however, he improved it significantly. He worked to make his own lenses and grinded and polished them, and it allowed him to see at a magnification of 8 or 9 times the original picture. This is compared to the spyglasses of the day, which only had a magnification of 3 times the original picture. He is responsible for discovering what is now called the Galilean moons, which are the 4 most massive moons of Jupiter. During Galileo's lifetime, all bodies were thought to orbit the Earth. Galileo did not agree with this, however. He included his own observations of the phases of Venus and the fact that Jupiter boasted moons that didn't orbit the Earth, which supported the Copernican system, which stated that the Earth and other planets circled the Sun. This was later found to be a correct statement. During Galileo's time, stopwatches did not exist. They did not exist until the 18th century, and they were small but reliable mechanical clocks. Galileo's clock, however, was a water clock, and this is described as a large vessel of water placed in an elevated position with a pipe attached that had a small diameter, giving a thin jet of water, which was then collected in a small glass during the time of the descent. The water was then weighed after each descent on a very accurate scale or balance, and the difference in ratios of the weights gave the differences in ratios of the times. This was measured with such accuracy that although the operation was repeated many, many times, there was no appreciable discrepancy in the results. In the early 17th century, Galileo makes a claim concerning the natural motion of a free-falling body. Galileo claimed that a naturally falling object will gain equal amounts of velocity in equal amounts of time. If correct, that means that 1. The object speed increases as it falls. 2. The rate at which it picks up speed does not change during the fall. However, Galileo found that it to be difficult to test any free-falling object because they move too quickly and it's too hard to record the motion directly. Because the 17th century clocks could not record the short times involved, Galileo tried to slow down the motion by replacing the falling object with a ball rolling down a gently inclined plane. In doing this, Galileo assumed that objects descending on an inclined plane speed up the exact same way that falling objects do. His reasoning behind this was that a ball rolling down a steep incline will pick up speed faster than a ball rolling down a gentle incline, but the way in which its speed increases will be the exact same. This made sense because freefall, he reasoned, is simply equivalent to a vertical ramp. The character of the ball's motion in freefall should be the same as the character of the motion of a ball falling down the inclined plane.
We started with a water clock consisting of a 5-quart jug with a flip open valve near the bottom. With the jug filled completely, we measured the time it took a marble to roll down an incline by weighing the amount of water that drained in the time the ball rolled down a ramp. Our measurements were in grams per centimeter with lengths of 5, 10, 15, and 20 centimeters. After several tests, we took the average mass of the water for each distance and compared that with the distance traveled. We discovered that when we measured grams per centimeter, we had a roughly linear graph with a slope representing acceleration in grams per centimeter squared. We also analyzed the standard deviation for each datum compared to the mean for its respective length. When we graphed the average velocities and connected the points, we found a maximum and minimum slope showing that the acceleration must lie between the two lines. We account error in our measurements to the accuracy in starting and ending the water clock in time with the marble, as well as not influencing the marble as we started it. To minimize these errors, we ran several tests, and with each test, we moved our hand down the incline away from the marble to release it.
Okay, so in order to minimize the error from delaying the ball, when I release it, I try to pull away from the ball down the ramp at the same time that I open the valve on the water clock, as I do it like this. And then when it reaches the bottom, I close the valve, and then I read how many grams on the clock, and I enter it on the computer here, and then I can zero out the scale by pushing this button, and then I can run it as many times as this will let me fill it.
Here's all the data we have acquired from our experiments. We took 25 tests at each length, and we used 4 different lengths equally spaced between 5 centimeters and 20 centimeters. All the water measurements are in grams. As you can see here, when the measurements at each length are averaged out, it creates a linear plot. This shows how the ratios between time and distance are proportional to each other. Here is a graph and data that shows the inconsistencies in our experiment. Because all of this was done by us, we cannot ensure that every drop of the marble and start and stop of the water clock is exactly the same every time. Because of this, there are some inconsistencies in the data we took.